So we've worked with the counting principle before, and we're going to utilize that to kind of help us with another topic that's called permutations. So remember, if you have two experiments that are being performed, the first one has m possible outcomes, the second one has n possible outcomes, then the way you can perform these two experiments in the order is m times n. So let's look at an example. Sally plans to enroll in 4 classes, 1 sociology, chemistry, economics, and humanities. In total, there's 7 sociology classes she can pick from, 4 chemistry, 3 economics, and 4 humanities. So all of these are going to fit their schedule. We want to figure out how many different ways can she possibly select her class. So we need to go through, and she has a couple different options for these 4 things. So I'm going to go ahead and kind of label what each course is. So for the first course, she can take a sociology, and she's got 7 options for that class that fit in her schedule. For the chemistry class, she has 4 different possibilities. For the economics, she has 3. And then for the humanities, she has 4 again. So each of these events, if we want the total amount of combinations we could possibly have, we just multiply them together. So there's 7 possible outcomes for the first event, 4 for the next, 3 for the next, and 4 for the last. So in total, she has 336 different possible ways she can pick her class. So pretty much to find the number of ways you can perform some type of thing, you've just got to figure out how many possibilities for each of them. So let's look at another example. A password consists of 2 lowercase letters followed by 4 digits. So we want to determine the number of possible outcomes for different passwords if first repetitions are allowed. So if you think there are 26 letters in the alphabet, so for those first 2 spaces it has to be letters. And then the next spaces are digits. And technically there's 10 because you have 1 through 9, but then also 0. So the password is going to look like the following. We're going to have 2 letters and 4 digits. Okay. So for this first option, we put a letter and a letter. And then in these options, we put a digit, 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 digit. Okay. So for the letters, because we can repeat them, you have 26 options for the first one and 26 options for the second, because I can put an A and then an A. For the digits, same thing. I have 10 options for each digit because I can use the same one. I can put a 4 in every space. So each letter has 26 options. And then each digit has 10. So if we want the total possible passwords we can make, we would multiply the 26 by 26, 10 by the 10. So if you do all that, 26 times 26 times 10 times 10 times 10 times 10, you have 6,760,000 possible passwords you can make. Okay? Now if we change this slightly, and now we're not going to allow repetitions. So if I use an H, the next one can't be an H. Same thing with the digits, I've got to pick distinct digits. The password's still going to look the same, so I'm going to have a letter, and then a digit, 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 digit. Okay. But now here, For my first letter option, I still have 26, but once I pick a letter, I now only have 25 to choose from for the second. So if I picked an A, I can't pick an A again, so I've got one less to work with. So here you have one less letter. Okay. Now for the digits, the same type of thing happens. You start out with 10 possibilities. You're going to use one and it's no longer an option. So now I have 9 digits to choose from. When I go to pick the third number, I can't use the previous ones, so I've got one less, so I have 8 possibilities. And then finally, I've used 3 possibilities. I only have 7 unique ones to choose from. So in here, each time, there's one less than before. Okay. So if I want to see what are or how many possible passwords we could have, we're going to multiply all these numbers together. So 25 times 26 times 10 times 9 times 8 times 7. I have 3,276,000 passwords. Okay. So now in these 2 particular examples, the order of the letter is actually given to us, but it doesn't necessarily have to always hold like that. I can put a letter first, I could put a number first, and I don't have to have a specific amount of characters. I can do more. So we could figure out a way to possibly also arrange these options. So a permutation is exactly this concept. A permutation is any ordered arrangement of a given set of objects. So you're basically permuting their location. So let's try an example. We're going to determine the number of ways you can arrange the following 3 pictures. So the order of the pictures matters. So we've got a smiley face, a triangle, and a little tree. One possibility is you flip the triangle and the tree, but you still keep the smiley face first. I could also put the triangle first and then put the 2 in any order I want. And then I could flip the 2. And then finally, I could start with the tree first, smiley triangle, and then flip the smiley and the triangle. So these are my only possible ways. In total, there are 6 ways to arrange the pictures. And one thing you kind of want to note is really, I've got these 3 pictures. I had 3 options for this first image. So for the first spot, there's 3 options. Now for the second spot, I've used one of the options, so we only have 2 pictures we can pick from. And then in the third spot, I've only got 1 thing left. So pretty much you can kind of look at these different things. I had the 3 options here. Now once I've picked a first image, I could put 2 different ones first. And then once I've used that second location, I only have 1 picture remaining. So I only have 1 option for the third spot. So in total, there are 3 times 2 times 1, which are 6 ways to arrange the object. The 3 objects. So this is something that's called factorials. So the number of permutations of n distinct items is n factorial. And the way we denote factorials is with an exclamation point. So if you want n factorial, It means you start at n, one less number, n minus one less number, and you keep going down to 3, 2, 1, all the way through. Okay. So let's just look at some examples. If you have 3 factorial, that's going to be 3, the next digit down, the next digit down, and you stop at 1. So you get 3 times 2 times 1, which is 6. So 3 factorial is the number of ways you can arrange 3 objects. If you look at 4 factorial, that's 4 times 3 times 2 times 1, which is 24. Okay? So you just go all the way down. One thing you can also note is this 3 times 2 times 1 is exactly 3 factorial. So one of the nice properties is you can pick off that top integer and you get the next number factorial. You can do it again, pick off the top integer, you get the next number factorial. But in the end, you're still going to end up with exactly the same number. And then likewise, if you have 5 factorial, it's 5 times 4 times 3 times 2 times 1. It's the same thing as you pick off the top integer and you get 4 factorial left over. You can keep pick off the 4, you get a 3 factorial. And in the end, you still get exactly the same number. There are 120 ways to arrange 5 objects. So we do have one special kind of definition we have, and that's 0 factorial. So 0 factorial we're going to define to be 1. So basically, if you have no objects, there's one way to arrange it. You don't. So it's a special definition. So let's look at an example. 7 pictures are to be hung on a wall. How many different ways can you arrange them from left to right? So you could absolutely set up kind of this number line where we have 7 options, 6 options, 5 options, 4 options, but the number of ways you can arrange 7 objects is 7 factorial. So you have 5,040 ways to arrange the pictures. Okay? So let's utilize this concept of factorials. We're going to do another example, and then we're also going to see a different definition that kind of pops up from this. So suppose there are 9 people in the math club. Collectively, we're going to put every person's name in a hat. The first person we pick out is going to be a president. The next person is a vice president. And then we're going to pick out a secretary. So we want to see how many different permutations are possible. So the reason it is a permutation is because that order matters. If you're picked first, you become the president, versus being picked third, you're going to be the secretary. So we've got 3 different positions. The first position that we're going to pick out is for president. The person that gets picked after that is going to be the vice president. And then after that is going to be the secretary. So on the first draw, you have 9 possible people you can pick from. For VP, now I can't have someone that's president also be vice president. So whoever I've picked is now out of the pool. And I have 8 people left in the club that I can pick from. And then finally, for secretary, I've picked out a president and vice president, so I have 2 less. I have 7 people that can be secretary. So in total, there are 9 times 8 times 7, which is 504 ways to select these different positions. Okay. So we kind of want to see if there's a connection between these. So it's going to seem a little strange what I'm going to do, but I'm going to kind of reverse engineer where this 9 times 8 times 7 came from. So we're starting with this. One thing we could do is remember we can always multiply the top and bottom by the same thing. So I'm going to go ahead and I'm going to multiply by everything that would make this be a full factorial in the top. So let's times it by 6, 5, 4, 3, 2, and 1 as well. But what we do in the numerator, we also have to do in the denominator. So this way, these extra numbers end up canceling out. And the nice thing is, by doing that, in the numerator, I've now got a full factorial. So I've got 9 factorial. In the bottom, 6 times 5 times 4 times 3 times 2 times 1 is 6 factorial. And so the connection we can kind of make is this is 9 factorial. There were 9 people that I could pick from. And in the bottom, the 6 is really 9 minus 3. Okay? So the way we can think of this in the numerator, there's 9 people. And then we have the number of people minus the choosing 3. So we're choosing 3. Okay. So we take from those 9 people, we're going to subtract out the 3 positions we're picking from. So in this particular instance, since I'm not selecting every single person, if all 9 were getting a position, there would be the full 9 factorial ways to do that. But the number of permutations possible when you're selecting R objects from n in total is given by this formula NPR. So the number of ways to permute these 3 people. So it's n factorial over n minus the R you're picking. So basically from this total collections of objects, we're going to arrange 3 of them. So in the previous example, from the 9 people, we're arranging 3 of them to figure out those positions. Okay? So let's try an example. A teacher has 10 students and she's going to select 4 of them to win a prize. If every single prize is different, so the order the child gets selected in matters, we want to see in how many ways can the prizes be awarded. So what we're going to do is we're going to permute 4 of these things. So from 10 students, we're going to see what's the number of ways we can permute 4 of them. So I'm going to pick 4 of them to get a prize. So this would be 10 factorial over 10 minus 4 factorial. So it's 10 factorial over 6 factorial. And if we want to simplify this, the 10 factorial you can write as 10 times 9 factorial. You can pull that off, get an 8, get a 7, and then all the way down to a 6 factorial. So it makes it nice. So the 6 factorials cancel. And so basically you have 10 children for that first prize, 9 for the second, 8 from the third, 7 from the sixth. So there's 5,040 ways she can give these 3 prizes away, or 4 prizes away. Okay. So let's try to think of another example. We want to see how many distinct ways can we permute the letters, which is going to be B, O, B. So we've got the word Bob, and we want to permute these letters where they are distinguishable by color. Okay. So the first thing we could do is we could leave it in exactly this order. So B-O-B. Now instead I could have this red B first, and then I could switch the order of the O and the B. So I could put the purple B and then the O. My next possibility is I could start with O, and I'm going to have 2 different ways I could do this. I could put the red B first, or I could put the red B second. I could put the purple B second, or I could put it first. So those are 2 more ways I can go through it. And then finally, I could put the purple B first, and then I'm going to have two different possibilities. I can put the red B first, I can put the red B second after it. Or I could put the O and the O here. So the main thing is, although these spell out exactly the same, these are exactly the same, and these look exactly the same in terms of letters, they're different because the letters are distinct. Okay? So these are all different because the letters are distinguishable. So really, there are 3 factorial, which is 6 ways to arrange them. So you have 3 objects that you're arranging, and each one is distinct. Now, if we can't actually tell the difference between these letters, so the B's look exactly the same, all of those cases that looked similar before are now the same. So you only have 3 possibilities. I don't have this case here, the OBB and OBB, because I can't tell the difference between the 2 B's. So now it cuts this in half a little bit. There's 3 ways when they're not distinct. Okay? So in the case we do have repetitions of different objects, so they're considered the same thing, the number of distinct permutations of n objects, where n sub 1 are identical, n sub 2 are identical, all the way up to n sub r are identical, is given by this formula. So basically the idea is if you have 30 objects, there's 30 factorial ways to arrange them. But if 4 of them are exactly the same, I'm going to divide out by 4 factorial. If a different set it has 3 that are the same, I'm also going to divide out by 3 factorial. So if you think of this prior example, I have 3 different objects, 2 of them are identical. So we arranged 3 objects where 2 are identical. So up top is the 3 objects and 2 were identical. So you divide by 2 factorial, which simplifies to 3. So you still get the same result. Okay? So let's try a harder example where we've got a few different letters that repeat. So we want to see the number of ways we can permute the letters of the word statistics. So the T's are not distinguishable, same thing with the S's and with the I's. So in total, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 letters. So there are 10 letters. So there would be 10 factorial ways to arrange that, but some of them are going to be exactly the same because the letters repeat. So there are 10 letters, of which we have 3 S's. So 3 are S's, 3 are T's, and then 2 are I's. So what we want to do is there's 10 factorial ways to arrange the letter. We're going to divide out by each of these factorial. Okay? So there are 10 factorial, and we're going to divide out by those repetitions. So 3 factorial, 3 factorial, and 2 factorial. So you count how many repeats there are, and you divide by that factorial. So let's try to simplify this. You can plug it into a calculator if you want. The 10 factorial is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3, 2, 1. So you can just write it as 3 factorial. And then in the bottom, we have 3 factorial, 3 factorial, 2 factorial. So the nice thing is one of these 3 factorials cancels. So we get 10 times 9 times 8 times 7 times 6 times 5 times 4. And then in the bottom we have a 3 factorial and a 2 factorial. Well, 3 factorial is 6. 2 factorial is 2 times 1, it's just 2. So we actually have the 6's cancel. And then the 2 goes into the 4 2 times. So the number of ways we can permute these letters is 10 times 9 times 8 times 7 times 5 times 2. So there is 50,400 ways to arrange the letters. So in this particular section, the order does matter. In the next section, we're going to see the order is not going to, and that's going to be a different topic called combinations.